Hello everyone, I'll explain the compression test on mild steel or cast iron, the procedure and how we are going to take the observations. So first thing is we have to take a specimen, whether it is mild steel or cast iron, and measure its dimensions. So we will measure the dimensions using a vernier scale. So I will show you the specimens. We can have different materials. So here this is aluminium, and this is brass, and this is cast iron, and then we have this is mild steel. So we can have different materials for testing this, for doing this compression test. And if you notice, the size of this specimen is very small, but to be precise, we will measure the dimension of this specimen, that is the length and the diameter, using this kind of a vernier scale. So how I will do this is, first I will measure the diameter. So I will hold the specimen like this, place it in between the vernier scale and push it. So we are getting something around 9.93 mm as the diameter, and you can measure it 2 times. So here I am getting 9.94. Then I will measure the length of the specimen. So I am getting it as 13.25 millimeters. So that is the length of this mild steel specimen. So we got the length and the diameter. So using the length and the diameter, we will determine the L by D ratio, and we have to ensure that this L by D ratio is less than or equal to 2. So this is to prevent bending failure, because if the length is too long as compared to the diameter, then this sample will tend to bend, and we don't want that kind of a bending failure. We want failure due to compression. So if we try to ensure that the length to diameter ratio is less than or equal to 2. And if we look at the deformed shape, so what happens when we load this specimen? Initially the original specimen has this kind of a diameter, and once the compression load is applied, so you can see here F, when we apply that load, it will get deformed. So obviously the length will reduce, and what will happen is, along the lateral direction, that is the diameter will increase. So this dotted line shows the deformed material, which will have a shorter length and a larger diameter. And this kind of failure happens in a ductile material. So if you notice, in the case of a brittle material, we will have similar shortening in the length, but what happens is there is a shear fracture plane which is formed. So here you can see the dotted line showing the shear fracture plane formed in the case of a brittle material. So we can perform this test either on a ductile material or on a brittle material. So as I showed, we have 4 different samples, 4 different samples of materials. We have mild steel, we have cast iron, we have aluminium, and we have brass. And out of this, we have 3 are ductile materials, and only the cast iron is a brittle material. And coming to the observations, what all observations we will note down? So first we will note down what is the material that we are testing, one of the above. Then we will note down the initial gauge length, L0 in millimeters, whatever we measured using the vernier calipers, vernier scale. Then we will note down the initial diameter, also we measured using the vernier scale in millimeters. Using the initial length and the diameter, we will compute the original area, A0, as pi d square divided by 4, and load at proportionality limit. So once we start the loading and we plot the graph between load and deformation, we will note down the load at proportionality limit. And we also note down the maximum load, F max, in Newton. Then we determine the slope of the straight line portion of the graph, which is also called as Young's modulus E in Newton per millimeter square. Then we'll determine the percentage contraction at fracture. So how much contraction happens, that is DC, and it is given as L0 minus LF times 100 divided by L0, where L0 is the original length, that is the initial length, and LF is the final length. And we also find out the percentage increase in area, dA, which is area after the test, that is AF minus initial area A0 times 100 divided by A0. And from the graph, initial tangent modulus of elasticity can also be determined. And finally, we'll after the test is complete, we'll measure the final gauge length, LP, LF in millimeters, and final diameter DF also in millimeters. Then final area, which is given as pi DF square divided by 4 in millimeter square. And then we'll compute the proportionality limit sigma p, which is given as Fp divided by A0, and we'll also determine the compressive strength as F max divided by A0. So these are some of the observations which we will get from this compression test, and based on these values we can determine whether the material has sufficient strength or not. And the kind of the data that you get from the universal testing machine, so you will get the load data in Newton, and corresponding deformation you will measure using the deformation gauge, that is delta L, and using these you can compute the stress, that is whatever force is there F divided by the A0 area, and you can also calculate the strain as change in length upon original length, that is deformation divided by the initial length. And using this values of stress and strain, you can compute the Young's modulus E, which is given as stress by strain in Newton per millimeter square. Thank you. Show you how to note down the observations. So initially we'll take for this case we'll take the brittle material, that is cast iron, which is shown here. So I am taking the specimen of cast iron, and I will measure the initial gauge length and the initial diameter using this scale. So what I will do is first I will measure the diameter. So I will tighten this, push it from the right side, and you can see the diameter is coming as 11.52 millimeters, and then I will measure the length. So that is 12.83. So this is the length and the diameter of this cast iron sample. This is our universal testing machine. Here the maximum capacity of the universal testing machine 1000 kilonewton, and this is there, and these are the controlling valves. Here controlling buttons are there, and this is the crosshead. This middle crosshead, this is upper crosshead, and this is the lower crosshead. Here we have a dial to measure the deformation. Now this is called as a deflectometer. Okay, this is our deflectometer, and come here. This is pressure releasing valve, and this is pressure given valve, and here our dial is there. No, the maximum capacity is 100, but now we are setting as 100 kilonewton. See, when it's 100, the least count is 0.2 kilonewton. Every small division count as a 0.2 kilonewton. Right. Now we can change it as 250 now. When it is 250, the least count is 0.5 kilonewton. When it is 500, the least count is 1 kilonewton. And when it is 1000, the least count is 2 kilonewton. Okay, see this cross-head buttons. When you press this one, this middle cross-head goes upward. Like this it will go up. And when you press this, it will come down. This is working in electric pressure. Like this we have to operate the middle crosshead. Okay. So now this is the specimen. This specimen should be placed here. Like this you have to place the specimen. And then move this same center of the torsion.
We can use that other one, this one.
That air gap should be leave because when it will touches that specimen, it will get preloading. No, we can't able to measure the load. That's the reason we should leave that portion, and then by switch on the universal testing machine, give the load. Switch on now. Closely increase the pressure. This is dial adjustment. When the base should fixed at specimen, at that time you have to set it as 0.
You can get it.
Stop.
Stop, stop.
Now set it as 0.
Stop.
load. Then we have to release the load here. So this is our payload load. Then we have to release the load here. So this is the sample which has failed, the cast-in sample. You can see the crack. So there is a shear plane which has formed. So the next step for our calculation is to find out the diameter and the length of this after the test. So I will again use the vernier scale to measure the diameter. So I am getting it as 12.44 millimeters, and if I measure the length, I am getting as 11.73 millimeters. So what happens is, after the load, the length decreases and the diameter increases.